So we group them into 4 or 5 questions. We'll start with those, and the panelists will answer those. Each one can comment, say for 5 minutes on each one. And at about 4:30 or so, we'll have open questions to the floor. Anyone can ask any questions they have. So, going to this. So the first question is, what are the current challenges in hybrid simulation? What are your suggestions to overcome them? What research efforts are underway to address those? So the question is behind you.
Go ahead. So definitely this is a very large question, and I think the biggest challenge seems to me. So we have developed a lot of good method, compensation method, integration method, and all kinds of methods. But I think a lot of people are, do not fully trust those methods, and they do not have confidence on those methods. And so the biggest challenge is to let people know, those methods are mature enough to be used in real application. They are not the scientific subject only. So more and more people should start to use. For example, MTS, we sold over 100 hybrid simulation systems, and not many are fully used. So that's the challenge, and we need to let people know those methods, solutions are ready, and they are good if used properly, and people should start to use them. People shouldn't think they are so complicated, and once people start to use, and then hybrid simulation will take off.
You represent.
Okay. Well, I think one of the challenges is similar to what you said, is of course the validation and the verification such that people can believe in the method, and it's not really a method, it's a way of solving problems, because you have the computation side, you have the physical side, and you're putting them together in a clever way. But what I think the really biggest opportunity or challenge is somehow to get the practice, adopt the hybrid simulation as a standard or as a way of qualifying things. Shahzad sitting in the back, I know we were thinking maybe IEEE 693 or something. They have to do qualification of electric equipment, and they have a standard for shaking table tests, which is fine.
Let's invite Shahzad also.
It brings funding to our lab to do shake table tests, but sometimes it's not doable, and it's just getting some kind of a specification body or a code body to believe in the method as an alternative, at least. It can be a good challenge to think about, and between Berkeley and other research institution and MTS, if we can push for that, I think we can really solve many problems that are very hard to do by doing everything on a shaking table or in a certain way of testing, at least having as an option, but somehow we need a framework that people can accept and believe in and trust. That could be a mix of challenge and opportunity and possible research solutions. We go back to you, or we go this way? Let's go back and forth.
Oh, okay.
And then we'll go to Andrea.
Well, a lot of vision for the future and how to use that technology to a wider variety of topics. So for me, I will probably go a little bit technical side. I would still think that this whole system integration thing, when you have so many physics systems, especially in the afternoon session, a lot of interesting applications, fully multi-physics, and you have a lot of physics laws in mixing with physical domain and cyber domain integration, all those technologies together. I think that's still something challenging but also interesting. It keeps technology moving forward. So I think we just ought to find more applications like those, very interesting ones, and then push them forward, make them more visible.
Maybe one thing I like to add to what was said before is maybe going back to more the big picture side is like we would really, I guess, create some better resources for people that are interested in hybrid simulation to go to learn, to see what has been done. I feel like there's a lack of that. It's hard to get to the information. It's difficult to see what has been done, what works well. Maybe not just things that work well, but also show a little bit where the challenges are and what the tricky parts are. So talk about that as well and how they were overcome. So some kind of maybe video tutorials, sort of a 101 on hybrid simulation, something like that, similar to kind of what the Sim Center is trying to do for other areas. I think that could benefit the field. So it's just to keep the interest and for people out there to better understand what it's all about and how we're doing it, and have this like unique place that they can get to get this information, and they don't have to scramble around, try to find the information and in many different sources. And so I think that could help as well.
Okay, I'll add something. So maybe it's also something to consider is to make the method a bit more mainstream type of thing. Actually, sometimes when someone is writing a proposal and when they're considering like testing types to use in their projects, they sometimes bypass hybrid simulation because they think it's difficult and it requires expertise and all that. So if the method becomes more easily doable and the learning curve is less steep and all that, that would make the method more applicable and more people could benefit from that and not get scared of it actually. So in that regard, what Andreas says is the beginning, so that people can use like resources and stuff to learn, and then develop a kind of a database and and sorry, one more thing to add is these comparisons between shaking table tests and hybrid simulation. They are kind of rare. To convince people that it's a reliable method, maybe those benchmark cases need to increase a little bit.
Yeah, I would go in the same direction as you, is that as users, as Polytechnique, some of the professors are really interested in going into hybrid testing, while others are pretty much comfortable in their older ways to do tests, so pretty much going, or still going into cyclic testing, things like that. Others are pretty much interested in going full-scale specimen. That's a major aspect for us. Stiff specimen, pretty much a complex system with multi-degree of freedom. We've been struggling like this for maybe almost 2.5 years to have this system working. That was our most challenging stuff to make this thing work. You guys develop a lot of techniques, so fortunately we can use those, but still we have to bring those all together and make the system work. That brings another challenge into this equation.
Sharsad, okay.
So I would like to support how it works. So yeah, I work with industry quite a bit, and I talk to these guys all the time. And sometimes they don't know that we've developed all these tools. And when we are educating them, so that's why we had several workshops during NIS operations for the industry. So they were excited to see that. Two shaking table setup with a cable in between two pieces of equipment. It was really exciting to see because you can see that two systems are having two different natural frequencies, and we have a non-linear cable connecting the two. And just continuing the same idea, so Slim had a slide about the substation that failed during the earthquake in China. So, and there is a way to test it, right? So if you have several shaking tables, small ones, we are talking about small forces between the cables, this is the way to go. Everything is modeled except the interconnected equipment. So only the cables are going to be physical elements throughout the big testing system, essentially. So, and it's never been done, and this kind of opens up a lot of possibilities. So all these methods and approaches and all these tools you and we developed all together, this will serve our everyday needs essentially, because we are working with the industry, trying to bring it, put it in the standard, develop something that will be realistic and close to the practice as much as possible. Thank you.
So you all addressed a wide range of answers were given, and some of these they're part of these recurring questions. You will see other questions. So,
You have to read them first.
so the other question that came is which other areas do you see hybrid simulation being extended to, and then are there any research efforts in those directions? Any of
Alex's approach is very interesting. So I would say it should be a lot of research in that field.
Yeah, let me. I mean, we have seen the last session. We have seen Earth, which is earthquakes, and then we have the wind. That's a lot, and we had the fire, right? And we had even the light. So.
water too.
Yeah, and the waves, the ocean waves. Yeah. So that's why I said it's really not a method. It's a way of thinking. Okay, you know how to model things. You know how to program things. You know how to solve differential equations, partial differential equations. You have tools to do that, and we know how to test things. So rather than trying to make the specimen so small, and then we run into similitude issues and complexity of doing. Scaling down things, you just think, okay, what is there I cannot model? What is there I know how to model well? And what are the issues of the interface, friction and whatnot, and how to resolve these things? So you can really do a lot of parametric study in so many fields with very little resources. And we need to do lots of these because we know every engineering problem has many sources of uncertainties. So you have to quantify these uncertainties. So one test will never do it, no matter how expensive it is and how detailed it is. You need a variety, repeat the same test multiple times so you can quantify these uncertainties. So it's not a matter of lack of resources, it's just what is doable and what is not. Even if you have all the funding in the world, you will not be able to run hundreds and thousands of the same test. But with hybrid, maybe you're not going to be able to run the hundreds and thousands, but definitely you can do the tens and maybe close to 100 too, in a short time with limited resources. Then really the sky is the limit. The daylight is it's not even a big deal. So, and just putting the hardware with the software in a smart way is what hybrid simulation is about. Then applications is boundless, from cars to aerospace to daylighting, building, modeling bridges under different kind of extreme loads. It just has to be adopted. So it has to be part of our curriculum. It has to be we have to teach it to students. So many things. So I think this workshop can be just the beginning of so many things to do, such that this is acceptable exactly the way we accept finite element or finite difference. And many applications ahead, you have to put boundary element with finite element because they are the best combination. There are so many examples where not just finite element is the best solution. You have to model this using boundary element, model this using same thing. It's a long answer. Then others. So who's next?
Yeah, I think I fully agree with you, and I think hybrid simulation is another way of thinking. Applications are endless. For example, right now the automotive, autonomous vehicle is really hot, and the people want to, design the self-driving, airport, and then the government require you need certain miles, millions of miles, before you can, sell the autonomous vehicle. And then to drive those many miles, you need so many cars and so many drivers and kill maybe so many people. And so then people think about the hybrid simulation, and then they buy driving simulators, and the simulators with the virtual environment, and only physical is the self-driving algorithm. And they buy many simulators and use robot driving and rank up the miles very easily and simulate all kinds of situations and without killing people and causing accidents. So that's an example, how hybrid simulation are used, and the answer is, it's used everywhere.
Like flight simulators training
Exactly.
pilots,
Exactly.
automobile simulators training.
Maybe we should connect with Uber.
Yeah.
Because I know they stopped the testing of.
Yeah.
We can do hybrids.
Will come. There is also a problem.
I'll go to the next one. This actually ties in with what Andreas had answered in the first one. How to help people just starting out with hybrid simulation, just so they don't reinvent the wheel. Some kind of a hybrid simulation wiki page, demo, videos, all that. Any thoughts on that?
Open Fresco Express. I let him answer.
Well, I already answered
You
that.
already answered it. Yeah, this is like real
Yeah.
time.
He wants
I-
a
I
formal
would-
answer.
Correct.
I would like to add one more thing to the previous question, actually, if I may. We've talked a lot about physical hybrid systems, but I think one area that is really upcoming is also things like network systems, where we can look at hybrid simulation in the way that you can do the same thing. You can have part of a network system being simulated and then other parts actually being physically tested. And so I think that's a big potential in that area too. So not just about the physical world in terms of mechanics, but also more about the electrical world, I guess, thinking about that and where that could go with hybrid simulation. So I think there's a lot of potential there.
Hybrid simulation stuff. Just to remind you.
Yeah, actually, I had an answer for the previous question.
Oh,
Change
too
it.
fast.
I mean, yeah, it's a quick answer, but I would just say immediately wind engineering in terms of hazards, because there is this potential and quite a bit experience in the earthquake engineering, and Nihari sites in the East Coast started to do experiments, but still wind engineering hybrid simulation is a bit not so mature, so I guess there's a big potential in terms of making hybrid simulation or bringing the hybrid simulation wind engineering to the levels of earthquake engineering. So that's one area that could be immediately done actually, because there are sites who are working on this. And the answer to this question is, as Professor Musalam said, maybe courses, designated courses on hybrid simulation could be something to start with, because if you don't have this type of things, I actually taught the experimental methods course in Berkeley last semester, and when I had the hybrid simulation lectures, the students did not go really in depth through all those material. So I kind of taught them and I gave them the material, but they really needed to do it hands-on just to learn it, and we didn't have that time. So if this is spread over a course, just focusing on the hybrid simulation, that can make people really trained on this. So rather than someone starting with a research project, let's say, if they take a class on this, it would be a good start, let's say.
From my point of view, I have one thing to do is start with something simple. Really, learn from it, make errors, send emails to people who knows what they're doing when they're doing this kind of research. So increase the complexity of the model and keep on learning from it. Okay. It's a learning curve. It takes time. You must understand exactly how your system behaves, what are the pros, the cons, and everything, how you can work around the things. And once you pretty much solve everything, then you're up and running and you can do pretty much as you like. So, but it's a learning process, so take your time. It's a time-consuming process, but it's definitely worth it.
Let me make a comment. I like the starting simple. When we do a finite element, we start by doing a patch test.
Yeah.
So we just need to develop the equivalent of a patch test in hybrid simulation, or benchmark tests, let's call it benchmark test. This way people can use that to test their algorithms, or to have a setup like NICE at Berkeley, for example, or the micro-NICE. And maybe that could be a way of learning if that can be copied. And I think it was copied in several of the NICE side when we had NICE. Turning it into the common practice and the common tools of education will be the way to start.
Oh, just
You
quick
can
on-
answer this or any other question.
Okay.
It's up to you.
About this, I think when NICE was active, there was a hybrid simulation wiki page created by Purdue, and recently when I visited again, I think it's done. I don't know if anybody is maintaining it at all. So I think it's always a challenge that how to maintain this intellectual property, right? How to we also heard a lot of a story that one expert PhD student graduated from a lab, then he took all the knowledge away, and nobody else can actually follow his previous development to do more in-depth research. I think it's a valid question. It's probably we already talked about to educate it, try to integrate it into some curriculum, create some benchmark tests, and the MTS. I know we also are trying to, Paul and Zach together. We are trying to make some introduction video about some of this. So I guess altogether, I don't know the final answer, but I think we will need a community trying to form together and all work together to make it happen.
Okay.
Can I?
Oh, sure.
I would just like to reiterate what I've sort of already said in the first answer, very first one, is when you look out there and you look at papers, publications about hybrid simulation, it always looks really nice. It always looks like everything is just working perfectly. And then when you try to do it yourself, you might find out that there is quite a few things that you need to consider and figure it out again. And so that's what I was kind of trying to say in my first answer, that we want to have not just the good cases, we want to also see what actually was challenging and how those problems were solved, so that people don't make the same mistakes again, or have to go through the same learning curve again. So yeah. The challenge with that is that we want to be careful not to scare people away. That's where it's difficult to bring those two together.
Open Fresco Express too would be a good lead-in for people starting out with them as well.
Okay. Ready for the next one? Okay. One of the questions several people asked will these workshops continue? The reports and videos are okay, but interacting with experts and seeing the physical testing was important. So, will these workshops be continued in the future in some way?
I will start since I have a little bit of authority to say yes. We will make sure. Actually, one of the objectives of peer these days is to hold workshops, not just for hybrid simulation, but for other things. And in my opening remarks, I mentioned some of the workshop we had already. Of course, we have our annual meeting and so on. This is the first workshop that is truly has some demos because of the nature of the topic. Most of the workshops are the format of a presentation and maybe discussion. I don't think we had a panel Q&A before, so that's also a little new. But continuing these workshops, I think we should. Hopefully, you agree with me that we should. We will make sure peer will be able to do that in coming years. As Selim said, we have a course in experimental methods, so we have interest in the topic. Part of it has to do with hybrid simulation. Maybe we can make it bigger if we generate enough teaching material from this course. I am thinking maybe we should consider an online course so we can open it up for other peer or non-peer institution. It is not just Berkeley that is part of peer. We have the pleasure of being the headquarters, but there are so many other great schools. They have great resources and great students. And also internationally, I mean, we had the pleasure of having some international attendees here. We like them. It's always not so easy to travel for long distance, but if you can access this material and your students and your researcher can access it and attend some online classes or watch a video, that can make the method more acceptable and propagate that. So again, long answer, but the short one is yes.
So yeah, at MTS and we, it's our interest to promote hybrid simulation and new testing methods, and we are constantly working hard to have seminars and like this to promote hybrid simulation. So last year we had a seminar in China, and there were 150 people attended that seminar, very successful. And in July, we are going to have another seminar at Swinburne University in Australia, and hopefully, you all are welcome to attend. And so definitely, MTS will continue the effort to have this kind of seminar around the world to promote hybrid simulation and other testing technology.
We'll move on to the next one. Since you two have agreed, I guess it's...
I'll agree also with that.
yeah.
When I said that's the first time to have demos, I meant as a peer workshop. But for NIS, we had so many demos before. But go ahead.
Yeah, we had that. So actually, what I'll tell is related to the feedback from the attendees. So for future workshops, so in these NIS workshops, we were having the survey where we were asking people, did you like the subjects, speakers, what other topics do you want to have covered, and so on. So and then this type of feedback helps preparing for the future workshop. So if we can do it somehow with this one for the attendees.
It would be great to send an email
Yeah,
with a survey.
Yeah.
So please respond to it and give us your opinion. You don't have to say everything was great. You can tell us what was bad so we can fix it next time.
We'll be sending you a survey, don't worry.
So another question, and I think he may have some more follow-ups on this, but there was a blind prediction contest by Peer recently. It showed a lot of variation in the analytical prediction. So are we really confident of the analytical part? And what does this variation mean to hybrid simulation? And you might ask a variant of that a little bit
So
later.
I'll just give a simple answer.
Yeah.
So as I mentioned in my substructuring presentation, so the starting point is actually you model the parts that you are confident with. So if the blind prediction results show variation, then it means we are not confident in modeling that, so we keep on testing it until we get confident. Let's say we are confident with obviously modeling elastic steel members, right? Columns and beams. So this type of elements probably need to, the confidence in modeling a wider range of elements need to increase so that we increase in our confidence in analytical modeling. But in terms of philosophy, so the objective is you model whatever you can model confidently. So in regards to that, this doesn't really affect hybrid simulation approach, I think.
In the blind prediction, if I remember correctly, you analyzed all the data. One of the big variation was in the change of the force in the pre-stressing rod. And this depends on so many details of the boundary conditions, especially under lateral loads. So that was a difficult problem. So sometimes we think, oh, that's so easy, it's just a frame, 2 columns. But there are lots of moving parts. So sometimes we overemphasize the variation without thinking of really the source of it. So how many moving parts were there? Is the boundary condition really well defined? So there are reasons why things had that much variation in it. Plus, of course, it has to do with the level of sophistication of the model that was used. However, there were some good results as well. There were people who managed to predict well blindly the results. So it depends on the assumptions of the model and how the different pieces were modeled. But as Salim said, we need similar, maybe blind prediction that may involve different kind of systems. There will be certain systems that will be easier to model than others with higher degree of confidence.
My answer is also simple. So you have to start with something anyway, right? So, but when you are confident, as Salim said, it's better to start with something you are confident with. So, but let's say today we had an elastic structure and TMD on top of it, right? Even that showed very good results. So, right? So in this case, you can find a good TMD for that particular structure, right? So this is it, right? It's very simple because it's elastic, but nevertheless, you were able to tune the structure to that particular TMD.
Mm-hmm.
Just to get the discussion going a little bit more, I think I'm gonna just take the other side for a moment. Everyone's advocate here, but I mean, I think the problem is maybe that people think that they're confident that they're modeling things correctly, or that they think they know, oh, I can predict this part well, but that actually is not the case, and they're not doing a good job. And so that's maybe where like a collaboration with like what the Sim Center is doing, like Frank walked in. And so what the Sim Center is doing is try to basically have some machine learning AI kind of capabilities that are helping the engineer making those decisions of how to model different parts. And that can help in terms of like deciding what can I model confidently, where can I do a good job, and then get that support on that side. Maybe that would be a good way to combine that with hybrid simulation. So I just wanted, I don't want to be all negative here, but I just wanted to quickly bring this up and just to look at that side as well.
Martin? Okay, you have.
No, I was just going to pass it.
Oh.
Go ahead.
Nothing much to say. It's like they did pretty much the same exercise in Toronto, where they, before testing a very deep beam, I think it was like 4 meters in height, 10 meters in length, and then they asked people to predict what would be the ultimate load. And I think that some of them predicted like 3 times the actual load that was resisted, and some of like they were just like 50% away underneath, and there was a big differences. So you always have the quality of your model, so in your results. And if you're starting with a bad model, you'll have bad results. That's about it. If you don't know what you're doing, then it's not because you can model something in a finite element model and gives you colors, response, and everything that it means that you get the good response of it. If you don't know what you're modeling, if you're doing a two-way slab and your model is coarse and you think that you get the bending and the column level and things like that, you're completely off the track. So don't do it. It's pretty much the basic. If you don't know what you're doing, you won't get any good results.
Okay. One question you answered in the first one is kind of a recurring thing. How is hybrid simulation being received or perceived outside the research community? Are there many industry partners or participants who are to something like this way of thinking?
I'm not aware that it has been adopted by some other than academia. As far as I know, maybe you guys know more since you have 100 clients. I would guess most of them are universities, if not all. So I mean, it's important to think of ways of convincing the practitioners and people in industry that it's a viable tool when you have the need and the resources to at least put it on your option list. Just one thing about the machine learning, previous question. When the computer science community decided to do the ImageNet challenge in 2010, their error on average was 28%. Was the increase of number of participants. 2 years ago, the challenge of 2016 had 3% error. So machine learning and artificial intelligence of computer with more data and more models and more larger community has the natural tendency to reduce the uncertainty. Of course, garbage in, garbage out. You assume you have well labeled data and you have, and then you can use machine learning and other sorts of learning to improve the confidence in the model. So I totally agree.
Sean, any comments on the industry partners?
As I mentioned, we have more than 100 hybrid simulation customers, but mostly they are universities and research institutes, and not many companies buy our hybrid simulation solutions. And but there's a trend, and for example, lately, since the earthquake in Japan and the government, set a new regulation for nuclear industry and the safety stuff like that, and they set the standard very high and the high frequency, high G test, and none of the traditional tables can satisfy that requirement. So no current tables, specifically for earthquake simulation tables can do the test for nuclear safety. So that a lot of industry like Shimizu and they got the big table and they couldn't do the test. And then they are seriously thinking about hybrid simulation, and they use hybrid simulation to satisfy the government requirement. So I think maybe soon or later, probably, companies will be serious about hybrid simulation, because reasons of this.
I just like the second, kind of like what Chuck had already said. I think maybe if we can put in more effort into talking to code committees and making sure, if you look at ASC 7 for design, right?
Yeah.
Then you have the regular design methods, then you have alternative approaches, and then you have the experimental testing. And if you look in ASC 7, then they're only talking about shake table testing for alternative testings. And so if we can basically bring this idea of hybrid simulation into these committees so that they better understand and they start buying into this, so that we can make this several code cycles from now, get this in there, then I think we'll have a lot more participation from the practitioners, and because then that opens up the door for them to do these kind of tests. Right now, because it's not in there, they basically can't do it, right? Because then they're saying, well, by code, if I want to do an alternative design, I got to do the shake table test. I'm not basically allowed to do the hybrid simulation.
Let me just say one thing. The codes for testing non-structural components would require you to do simulation to compute floor acceleration, let's say, and use that as input. That's a hybrid simulation, but it's a hybrid done separately. What if the non-structural component was too heavy that it influenced the structural response itself? So it's just a matter of doing it online or doing it at the same time. But there are tests that you have to do, pre-test analysis to determine the input to the test, like in testing certain equipment or facade panels that are non-structural. So still, again, the test will be as good as the input to the test because it comes from a model. So putting the two together and being able to put hybrid as a standard method doesn't seem very far out, because there are examples like that, or at least similar.
Actually, as an example of a company, the Calway team we just presented, they are a company.
There you go, yeah.
So, and the thing is, they're actually a startup, and they have their origins from a university environment. And I think these type of startups are getting increased these days. So people are more collaborating with the academia in terms of startups. So that gives a chance to use this method, which is close to academia, more in practice, based on the current set of startups.
We did only one test for a client, a commercial client. It was a shock transmitter or a bridge damper. They had both solutions, so we booked the real-time system, and we pretty much tested, but it was a single degree of freedom. That was the best they could pay for, and pretty much they weren't not quite interested by this, but we offered them this, and we asked a master student to be involved into this project. So pretty much it came more from us than from them. But that's about it that we have done for the industry on our side.
It reminds me a bit of isolation. In 70s, it was in the universities, Professor Kelly and others. Then in about 80s, it kind of started. Then 91 got into code, and now there are 10,000 odd elsewhere, not in US, but perhaps hybrid would have similar success as well. So now we'll have open questions for everybody on the floor, which some of them are already reflected in these 6 that were asked, but please feel free to ask the panel questions.
Kind of similar to the 6 questions we had, why the industry is not picking up these ideas, like you mentioned, mostly it's in academic circles. Isn't it true that when, for example, they're designing a 30, 40, or 100-story building in a big company like SOM or one of those fancy places, unless and until you offer them this technology at the very start of their design process, they're not going to listen to you, isn't it? I mean, they're going to say, well, we already have scheduled all that, and what are you talking about? And then, plus coupled with the discomfort of not knowing control theory and a few other unknown areas unknown to civil structural engineer. If you mention control theory to a SOM civil or structural engineer, they say control theory. I don't know what, I haven't done it. I know this exists. So the fear of the unknown is part of the problem. So how do you really overcome that fear, and how can people like yourselves, convince them that this would be beneficial for a major project or even a semi-major project, and that in addition it will also be something that if they don't use, they'll have a big dollar loss. Unless the industry or the big consulting firm or a big organization or government is convinced that if they don't do it, they're going to have a $500,000 loss or a $500 million loss or something, only then they listen to you. And if they say, well, no, this is a nice thing for you to use, we have all the technology, if you use it, it'll be very good for you, you might improve by 5%, this or that, or in a far out case where the plane is about to hit a building and you have fire conditions like World Trade Center building, and they'll say, well, that's a once in a blue moon, we have already controlled that kind of activity, and now chances are no more planes are going to hit building in the United States, for example. It becomes a very difficult selling job. So how do you really convince those potential clients in the government or the private sector to really buy off on what you're doing, what you have to sell?
Well, I can just, I don't know if I have an answer on how, but probably the fear is not really control theory. And by the way, SOM has very good engineers, probably they all know control theory, but it's like, when you do a shake table test, when you do quasi-static test, you also use controller, you use data. The beauty of hybrid simulation is you are not using anything you don't use already in if we call them standard or traditional tests. It's just we talk a lot about control because really the unknown here is mixing computation with physical model. Because whoever come to the lab, they come to you usually because they are not trusting the computational model. So when you come and tell them you're going to mix the two, that was the fear. They come to you to test it so they can look at it and poke a hole in it or touch it. So now usually the fear is in that mix.
I see.
And which go back to the original point is how confident we are in the computational part. That's usually what turns off people who come just to you to test something. Even though we use the same equipment, we use the same, nothing special.
Isn't it true that unless you show that they're going to lose X number of dollars if they don't implement this idea,
Yeah.
and that becomes a very difficult exercise for the poor researcher on the campus.
Yeah, the big selling point could be, look, you're going to give me $100,000. I don't think we get $100,000 to do one shake table test.
Yeah.
I can take the $100,000 and give you 100 hybrid simulation tests. Maybe that's a good selling point, that it become a cost benefit. So even if there are uncertainty, we're going to run this thing for you 100 times. in the 99 run, we better know what the heck we are doing. At least we can correct or learn from the previous 98 runs. So that could be one selling point. I don't think we ever did that. We tried to do that with the electric equipment.
Nice.
Is that we can do parametric study and so on, and we can do that in an effective way, cost and time. That could be a way of convincing.
I have
Can I make a quick response to in that? In 1970, a major bridge in Melbourne fell down 3/4 way through construction, and whilst it was partly engineer error in the construction phase, it was really that they hadn't thoroughly analysed the high stresses that occur in a partially built building. And back in 1970, it was the early days of FE. It was, in fact, the methodology was just starting. But one of the outcomes from the very big court case, and that's the big stick that you were talking about, was that there was an obligation on all engineers to use current technology and current technology methods. Just because you used a slide rule to do all the calculations and design the bridge wasn't enough. There was enough technology available that they should have used, and that was an interesting finding in a Royal Commission, which is the concern that big companies don't like to be litigated.
Yeah.
Yeah.
when industry comes to Polytechnique, they bring the ASTM papers and say, I want to test according to E9 or something like that.
Yes,
So they want state-of-the-art novelties. They don't want to hear about this. If there's something wrong afterwards and you have tested and this test was not approved, then they're in big trouble. So pretty much you have to make the hybrid testing being approved by codes.
Yeah,
Mohammed, you had a question at some point? Yeah?
Yeah, it's just like a logistic actual question. It has to do with the feedback. Like I think like a great opportunity here is to have like interaction with the researchers, and maybe you didn't have the chance to talk to every individual. So sharing a list of the participant and the contact information might be helpful also for future communication, especially from the MTS side. We can get list of the people from MTS, so that when we have questions, we know basically who is the right person to ask the question. So I think a list of participant and contact information would be helpful.
Paul, Zach, you want to respond? Basically, he's asking if we can distribute the participant list and relevant people at MTS to talk to.
If people are willing to have their names circulated, yeah, we can do that. We'll probably, like I said, we're going to be issuing surveys and other communications after this. We can query you, and you can indicate whether or not you want your name shared. So.
Yeah, we'll certainly share all of the MTS employees that you've seen here today as well. So.
Hi there. This question goes mainly to, I think, Andreas Schellenberg talked something about errors, and Sean Gao. So you mentioned a bunch of like error sources, but there is something that we've seen recently for numeric analysis. So at UNR we work now a lot of problems for impact. So like impact of a bridge on abutments, tsunami impact on structures. So very transient phenomena. Okay. So we've been using explicit codes to solve those problems. So one of the issues we have seen is that when you run those problems on different hardware, you get slightly different results. And when I say slightly, well, sometimes can even go 20%, 30%. And the problem that we realize with explicit is that you actually don't do any iterations, any convergence when you run numerical. That's the problem with the explicit. What you do is go to very small time steps, okay, in order to when you have that nonlinearity there happening, so you go very, very small and you assume something and you hope you're close enough. So we use like time steps to 10 to the minus 7, 10 to the minus 8. Problem with that is that error can accumulate through time steps. In numerical, I'm talking about purely numerical. And if your hardware is different and it can, for example, store different number of digits, let's say 16, 23, whatever, you end up having a different solution at the end of the nonlinear problem. So have you guys had this issue with hybrid simulations? Because I see that you also use explicit, and we even start doubting our numerical analysis just because of that problem. So how do you get to try your hybrid simulation when you're still using explicit analysis?
Yeah,
Is
we're
this a
not.
sort of error that you should consider, or you have considered, or?
Yeah, we haven't really seen that problem because when we do explicit for hybrid, we're not going to these really, really tiny time steps. Because if we would go into these really, really tiny time steps, we will face other issues with like actually controlling actuators. That will, when we send such small increments of displacement, the actuator will actually not move. So we are actually not doing those when we're talking about explicit methods in hybrid, we're not doing it at these very, very small time steps that you require when you do these impact or blast phenomena.
Okay.
I don't know if you want to add something to that.
Well, not really. I mean, yeah, it's. I think it's a different. So ours is more like structure dynamics problem. We are mostly talking about it's the frequency range we are looking at. It's probably different with the impact test that you
I'm
are
just trying to
interested in.
see if we can expand hybrid simulation to impact problems, not just like everywhere. I mean, your time step gets very small, and the issue is time scale and how do you do that real time.
Yeah.
And you cannot. So
It's going to be tough.
Mm.
What is impact?
maybe that's good for thought for the future. So. Thank you.
So you guys use a very small time step, right?
Yeah.
So did you have
1,000
a
hertz.
problem?
1,000.
Yeah. Oh, for the rigid.
Yeah.
Talking about what here, real time or integration method? We use explicit. Yeah.
Yeah.
Yeah. Modified Rosenberg.
Very small integration step size.
Yeah.
So any problem?
Milliseconds. No.
Yeah, but that's a whole like the order of
We
three
use the clock
magnitude
of the
difference
system.
than
We use
for
the clock
four,
of the
what you
system.
say.
Yeah.
The manual.
Mm.
Question for Dr. Shangao. You were using words like numeric, structural instability, I think, somewhere in your algorithms and things.
Okay.
And I was assuming that you were referring to really numerical instability that start to amplify some numbers and that create hazard for your jacks and the control systems. Would that mean that the hybrid simulation would not be suited for structures that are subjected to forces that actually create, honest to God, real diverging deflection time relationships where you have a real structural instability that the structure is supposed to develop under a given forcing function, and you're trying to really limit that. So in reality, it's supposed to have become dynamically unstable in this, in the traditional sense, but it's creating danger for the system getting damaged. So that means structures that develop dynamic instability, not numerical instability, but real dynamic instability, meaning diverging deflection time relationship, like flutter type. And then hybrid simulation should not be used there because it's dangerous for the apparatus?
Oh, well, so first, I think my stability analysis there is actually from a dynamical system perspective. So it doesn't take into consideration any space domain, time domain. You need to do discrete time instead of a continuous time. Mine is just pure system level. So it's just equational motion. I don't have it's just from that perspective, it's just your structure system itself should be a stable system, right? Because damping, that's the purpose of damping. Whenever you give a free vibration, it should damp out. Eventually, it should just go stop on some point. But some of the other systems, which are not like an active system, like our actuators, for example, those systems have other dynamics. And if you don't really, especially if it's a closed-loop control system, if you are not careful enough, that pole shift to the right half plane, and that actually give you a unbounded behavior. So it's going to increase exponentially with respect to time. That's the stability I was talking about. So I know, like for example, the different numerical integration solver could also have causing stability issue, but I think in your case you said there are some system which are intrinsically unstable.
Yeah.
I'm not sure how what type of system is that.
For example, like a column in the cargo bay of transatlantic, cargo.
It's basically the example I showed. So it's really, I mean, the structural collapse example that I showed in my small component application presentation. So we can do it. And then the hybrid approach is actually a very nice, safe approach to do this. So these two things are sort of, in my mind, that they're independent. I mean, we obviously got to make sure that we don't have instability because of control, because of errors. But once we can do that, and we minimize that potential of having instability, then we can actually look at structural instability on that level. So then we can look at collapse. And we can simulate that, and we can have safety on there, because we can have the actuators say we're not going to move any further than this, and we're going to stop the test. And so it's actually a very nice approach to look into structural instability.
So your system would allow diverging deflections up to a certain point, and then you have to put an end to it.
And then you stop it.
I see. Okay. Very great.
All right, thank you, panel. I think we have to wrap up there. Thank you. Can we give them a round of applause?